Welcome back to our system design series. Today we are going to explore another core concept in distributed systems, which is consistency. Consistency is crucial when building reliable distributed systems, and it's one of the most important factors to consider when designing for data integrity and user experience. So, what is exactly consistency? In context of system design, consistency refers to the idea that all users see the same data at the same time across the system. Essentially, when data is updated, consistency ensures that all parts of the system reflect that update correctly and quickly. Imagine a shared document that you can or you and your colleagues are editing. If one of you makes a change, you both need to see the change immediately. That's consistency. Let's take an example to understand that. Let's say that we have a social media application and we have a client that sends a request to a server. Basically, let's say that we have a client that update create a post, and we have other clients. Let's say that we have a client one, like client two, that will try to read this post, and we have client three as well that will try to read the same post. So when client one, when client one create a post and client 3 and client 2 try to see the post from the server, you basically see this exact same post. However, when the client also not however also when client 1 try to update or edit the post, okay, like change the title, change the name, remove an image, or whatever it will be, if our system is consistent and has high consistency or strict consistency, that means that client 3 and client 2 and client 1 as well will see the updates of the post that client 1 did at the same time. So all nodes and all clients see the exact same data at the exact same time. In distributed system, consistency is often discussed in in context of cap theorem, and we will talk about what is a cap theorem in in a bit in other videos. But let's just say on high level cap theorem, which states that a distributed database or distributed system can only provide two of the following three guarantees: consistency, okay, availability, and partition tolerance. And we will talk about what is a partition tolerance in the next video. But for now, let's only focus on the consistency. The trade-offs here are crucial to understand if you prioritize consistency, and you might make sacrifice in availability during times of network partitioning, meaning that the system may become temporarily unavailable in order to maintain consistent data. So there are two primary types of consistency. Consider a strong consistency and eventual consistency. Let's talk about them. So first, let's talk about the strong consistency. The strong consistency means that after an update is made, every read request will reflect that update instantly. This type of consistency is typically required in systems where data accuracy is crucial, such as financial transaction or booking systems. However, achieving so strong consistency can be challenging and may result in a higher latency, or also can affect availability. So the example we did talk about before, do you think it's a strong consistency or eventual consistency? Because we say that once client one edit the post, all the clients will see the exact same post at the exact same time, instantly from the point that client one edit that post. Try to think about it and give me give me that in the comment section below. But let's see right now the this example would say it's a strong consistency. Let's talk about eventual consistency. On the other hand, let's say that the client one edit the post, okay, and when the client one edit the post, maybe client 3 can see the edited post and client 2 see an old version of this edited post. And you can see, you can think about, for example, a post that has, for example, 100 likes, okay, it has 100 likes. Maybe client 3 can see 101, which is 101, and maybe client 2 see like 102 because there are two people add more. And our system has eventual consistency, so that means that it allows some delay before all nodes reflect the latest data. So maybe it will take, for example, client 3 a little bit more time to reach 102. So on the other hand, as we said, eventual consistency allows some delay before all nodes reflect the latest update eventually. Latest update. So eventually, all nodes will be consistent, but there might be a short period where different parts of the system show different data. This approach is often used in distributed systems where high availability is more important and temporary inconsistency temporary inconsistency are acceptable, for example in a social media application. So to achieve consistency in distributed systems, there are several approaches and techniques that we use. One of common strategy is to use like consensus algorithms like Paxos or Raft, which ensure that all nodes agree on the state of the system. Another technique is locking mechanisms, which prevent other processing from accessing data while update is processed to maintain consistency. And we talk about what is consensus algorithms and what is locking mechanisms in the future. However, consistency comes with the trade-offs. Designing for strong consistency can lead to increased latency and reduce availability, especially in distributed environment where nodes may be far apart, or the network may be unreliable. This is why understanding the specific requirements of your system is crucial. For some applications, consistency is non-negotiable, while for others, a bit of inconsistency is an acceptable price to pay for higher availability or lower latency. So that's it for this video, and in the upcoming video we will talk about the partition tolerance. So stay tuned. If you like this video, make sure to subscribe and hit the notification bell so you'll never miss a video, and see you guys in future problems.